Hello everyone, today we are going to dive into more advanced topic about ECS. So I hope you followed along the series and you did try to implement some of the features we will do today on your own, because it's by doing it yourself that you will learn the best. So if you have not yet tried yourself, you can go back to the previous episode if you want and try it yourself. And if you have followed along the series, we have covered the basics of ECS. We can dive into more advanced topics, such as the BlobAssets, aspects, and the different types of jobs that ECS offers. And at the end of the video, we'll even have a small teasers of the next episode about operating ECS and monobehaviors GameObjects at the same time to have VFX in this episode and in the next episode animations. So let's dive into it. You can, as usual, get the full documented code in the GitHub repository linked in the description below. And today we have the 6th folder, Shoot to Kill, where we will implement logic to spawn projectile from our towers and kill our enemies. So we'll implement 3 types of projectile. The first one, the simple one that just killed the first enemy. The second one, which is a piercing projectile that can hit several enemies. And the last one, a guided projectile that is able to follow the enemy. As we go further into the series, there are some stuff that we will need to implement again and using the features we've covered in the previous episode. So I will skip over those and only highlight the new features that we will implement, or the new tools that we will use to implement those features. But you can see everything in the GitHub repository linked in the description below, like I said. First up, we can open in the scene the shoot to kill scene, and we have the shoot to kill subscene, which contains our 3 towers. So we can see here the 3 towers. And we actually have 1, 2, 3, 4, and 5 enemies. And the 5th enemy is in a sphere, is encapsulated within a sphere because the sphere needs to move. So I'm using the pass follow we implemented in the second episode to make the little slime monster move. And then we have our 2 waypoints so that our slime can navigate between the 2. And that's it. If we look at the tower entity, we have the cannon authoring, which is the main authoring component we will view today. We actually have 2 other authoring components, but they are very simple. For the cannon authoring, we have a new feature, which are the BlobAssets. So until now, what we have seen is to store data about our entity. We store them in components, IComponents data or IBufferElements data. And this data is replicated for every entity. So it's great for data that is specific to that entity and that can change at runtime, like the health of the entity, the position of the entity, and so on. But for our towers, we will have some data that is just to configure the tower, like the fire rate, the range, and so on. So this kind of data doesn't have to change at runtime. It's static data, static configuration data. So it would be a waste of memory to have to replicate that data for every tower that we spawn into our scene. So what we will use for that is BlobAssets. So as you might have guessed, the BlobAsset purpose is to be able to share some data between different entities. And that data needs to be read-only. So for our tower, we will have some data that will be dynamic, meaning that we will need to update it at runtime, and some data that will be purely static data, like the range of the entity, the total time between each fire or each shot. So as usual, the first thing we do is to get the baking entity, and in that case we just need it to be renderable, meaning there is a position in space but the tower itself does not move. We need to have some physics collision filter, so this will be used to detect our enemies. So we will perform, as we will see in one of the systems, we will perform an overlap sphere like we did in the previous episode. And we will find the entities that are flagged as enemies for the tower to target. So this is part of the static data for the tower. And actually, before we go into the dynamic data, let me put it at the bottom. We are dealing right now with the static data. So the static data or non-dynamic data will be stored in a BlobAsset. And the BlobAsset cannot be stored directly into a component. So we will need also to create a BlobAssetReference that will hold the BlobAsset. And the BlobAssetReference will be put into a component. So let's first, we declare a BlobAssetReference of type canonConfig, and the canonConfig is just a struct that contains the data that we will need for configuring our tower. So fire rate, so how many times per second we will shoot a projectile, the collision filter that we will use to detect our enemies, how far can we detect an enemy, and offset to be able to spawn the projectile at an offset based on the tower position, so that it's spawned at the top of the tower and not from the middle of the tower or within the tower. This is just a struct, and we need to populate it, allocate some memory space that will be shared between entities. So to do that, we create first a blob builder. We can use the allocator dump because it will just be used within the context of the baker. It doesn't need to be persisted. And we create through the blob builder construct root of configuration data type. We basically here are allocating the necessary memory to be able to store the information about our canon configuration. Note here that we are using the ref keywords. So we are dealing with structs and we want to actually manipulate the memory of the allocation we just did. So that's why we are using the ref keyword here to get a reference to the struct, so the memory allocation of that struct. Otherwise, if we didn't have that, we would actually be modifying a copy, also another allocation of that struct. We can allocate all the data we need for that. And here I'm doing an offset based on the position of the tower and a position of a game object. So if I look back at my tower, I have the tower itself and I have the projectile spawn point, which is another game object, an empty game object that is placed relative to the tower. So I just compute the difference in position to get the offset between the two transforms. And last thing we need to do is from the blob builder to create actually a blob asset reference that will create a reference to our blob asset and that we will be able to put into our entities or into our component for our entities. Note here that we are using the persistent allocator because we need this memory allocation for the canon config to be alive for the duration of our game. So for as long as our game is running, we will need to be persisting this allocation or persisting this data. So here, what we are doing is creating an allocation of memory, setting some data into that allocation, and preparing a reference that we can keep into our component attached to our entities. If we do that for every entities that have this authoring component, we will still be duplicating the data for every entity. So to avoid the duplication of the data, there is a concept that is provided by Unity ECS, which is the Blob Asset Store. So we need to add a reference to our configuration data into that Blob Asset Store. And we do that by calling the add BlobAsset method, passing in a reference to our BlobAsset reference. And as an output, we get an hash. So basically a unique identification of that BlobAsset. If we had another config, canon config with a different fire rate, for instance, it would be a different value for the hash. So it would not share the same memory for those two configurations. And then the last thing we do is to create a component. So that's a IComponent data that we have here and that stores our blob asset reference. of canon configuration into a simple struct component that we can attach to our entity. Here, I've added in between another way to do the same thing, because here what we are doing is to build the BlobAssetReference for every entity that creates or that has the authoring component. So if you have complicated BlobAssets to create and to instantiate, it may take some time in the baking workflow and it may be not very efficient. So in that case, what you can do is find a way to pre-compute your hash or to use a asset GUID. So for instance, you could find a way to use the asset GUID for a scriptable object, for instance. And in that case, instead of just adding or creating the BlobAssetReference and adding it to the BlobAsset store, you can first try to get a BlobAssetReference based on the hash. So you could use the GUID of the scriptable object, for instance. And if you manage to get the BlobAssetReference, fine, you can use it in your adding a new component for the entity. And if you didn't find it, you can create your BlobAsset, so do the same thing as here, and then add it with a custom hash, so using the GUID that you were looking for into the BlobAsset store. And then the last thing we do is to add the dynamic data, so the non-static data for our entity. And here we can see that we are reusing the fire rate. So we have the fire rate into the static configuration and the fire rate that is used. But this one is used as a timer. So we will see in another system that we will basically decrease that timer and we will reset it once we have shot to the value from our BlobAsset. So we have two parts. We have the dynamic value that is changing throughout the duration of the game, and the static configuration that allows us to restart the cooldown. And the second dynamic data, so I will say dynamic in quotes because it's not really dynamic, it's the projectile. So we are getting an entity from the prefab projectile. It's a dynamic because it needs to be able to move, but you could tell me that this entity does not change during runtime. The tower will always fire the same projectile, so it could be considered a configuration or static data. The issue is that the blob assets, so what we built here on the top, does not support entity remapping. So that means that the entity reference we get here is only valid during the baking of the authoring component. It will not be valid if we store this reference directly into the blob asset. It will not be valid in the runtime. You can have a more detailed explanation about that on my other baking videos that I've already referenced several times throughout the series. And I actually already touched this point in a previous episode. So when you do a get entity, you get an entity reference that is only valid through the baking workflow and is not valid in the runtime. The reason why you can do it into a component data or an IBufferElement data is that Unity supports entity remapping for these two component types. So as part of the component definition, if there is an entity field, Unity will detect that and it will be able to remap the entity in runtime to change the entity reference within that component for it to be the correct entity. So keep in mind, if you want to get an entity reference associated to an entity, you need to store it into an iComponent data or IBufferElement data. You cannot store that into a blob asset. So now let's see how we can use that blob asset to actually spawn our projectile. So if we go to the projectile spawn system, here I'm doing an ISystem as usual. I'm requesting some component lookups and some singleton data to update my system. So same as last episode, I'm getting the singleton data, updating my lookup, and I'm doing a system API query using a for each to be able to gather the canon data. So this one is the dynamic data that I'm using with the time to next spawn and the prefab I need to spawn. The local to world component, so the position of the tower itself. And the last thing I'm getting is the tower config BlobAsset, which is actually the component that contains the BlobAssetReference to my canon config. The first thing I will do in the system is to decrease the time to next shot. So I'm using the tower data here, so the ref RW canon data, decreasing it by the system delta time. And if the time to shoot has not come, we just continue the loop and update the next entity. If we have reached below 0, the time to shoot our projectile has come, we will need to reset the next time to shoot, and we will also need to find the target and spawn the projectile and pointing it towards the target. To get the reference to the blob asset, we will need to get the tower config value read-only config value, and we need in that case to use also the reference keyword. If we don't use the reference keyword, it will not work. Next, we will need to check if we have an enemy to target, because if we don't have an enemy to target and we won't shoot, we won't reset the timer. So the first thing we do is to declare a closest hit collector. This will allow us to get the closest entity to our tower. And to find the closest entity to our tower, we will need to perform an overlap sphere operation using the tower position, the range of the entity, the collector we just declared, and the filters we have in the tower config blob asset. If we didn't find a hit, we continue to the next entity. If we did find a hit, it means that we have an enemy. So we can reset our timer to the firing rate, so the time to the next shot. And we can use the entity command buffer to instantiate our prefab, set its position based on the tower position plus the offset we have in the tower config. And last, to orient it towards our enemy using the position of the entity we just spawned and the position lookup to find the position of our closest enemy. So here we compute the values and here we set the values through the command buffer. So with that, we have our tower firing into the direction of our enemies. And we can look at the next system that will take in charge moving our entity. Here, for this system, I will be using one of the jobs that is provided by ECS. So this system will allow us to move our projectile in parallel or in a multi-threaded manner. The first thing we'll need to do is to get the position as read only, because we will need to have the position of our target in the case of the guided projectile. We will update that lookup as part of the update of the system, and we then schedule our job like we did for the trigger event job. In that case, we don't need the physics simulation, so we just have as parameter the state dependency that we reassign after to the state dependency. So this dependency, again, you can have a look at my other video about the job system in general to understand how the system of dependency works. But basically, it's just there to make sure that two systems that work on the same component and same data don't overlap each other and don't run in parallel. If one is in read only and one is in read and write, we would not want to have a race condition. So that's why the dependency system or dependency management takes care of it for us. And here what I'm using is the IJobEntity. And the IJobEntity is an interface to create a job as part of the ECS framework. And here I'm using the delta time, the position, very similar to what we had for the trigger event job. And here we have an execute method which takes in a projectile aspect. So we'll see in a minute what this is. And actually we could take in other parameters. If it was a read-only parameter, we would put in and the type of data. So here, for instance, Canon data. If it's read and write, we would use the ref keyword and put in, why not, the Canon config component. And if it was a dynamic buffer like the waypoints, we same thing could put in dynamic buffer for the read only for the dynamic buffer of waypoints, and I need a name, or ref if we wanted to read and write from that. But here what I'm using is something a bit different. It's an aspect, and an aspect is another type of struct that implements the IAspect interface, and it's a wrapper for a set of components that can be manipulated in the system or that have a coherence between them. And it allows the developer, so you in that case, to provide high-level method or to hide some of the complexity of the component management. So here what I'm doing is I just provided a method to say, okay, there is a projectile and that projectile can move. So to move the projectile, I need two things, the time and the positions of, or the component lookup positions. And to perform that move behavior, I actually need 4 components. I need the guided component, which is actually a component that I can enable or disable. I didn't use the IEnable component, but I could have for this one, for instance. The speed of the projectile, the target of the projectile. So if it's a guided projectile, I will have the target of that projectile to be able to follow it. And actually that is something that I've set in the projectile spawn system, and the position of the projectile itself. So here, take note that I'm using the local transform of the projectile, but I'm using the local to word component lookup. If we needed the same type of local or the same type of component, I would need to remove it from there and use the read and write version of the component lookup instead. But here I'm working around it by not using the same type of components. And then I'm performing my move logic. If it's a guided projectile and there is still a position, so here what I'm checking basically is to make sure that my target entity is still valid. If that's the case, I'm rotating the projectile towards the target, and then I am moving the entity forward. Basically, if the guided projectile has a valid target, it will turn towards the target and then move forward towards the target. If the projectile no longer has a valid target, meaning the target has already been destroyed, it will just keep moving forward. Here in the aspect, there are several things you can use. So here I'm just using the read-only and read-ref-write, but I've actually put everything that you can use within the aspect. So you could also have an entity field that would be the entity you are iterating on for that aspect. So the entity that is associated to that particular lead, speed, target, or local transform. That can be useful for using into command buffers, for instance, or to use as part of the component lookup read-write if you are using a component lookup. The component lookup cannot be itself referenced here. It needs to be passed in as a parameter of the method you expose. You can also have ref read write and ref read only. You can also have the enabled buffer. One particularity for dynamic buffers, you don't again put in ref read write or ref read only, just like for the system API queries. So you need to access directly dynamic buffer. So that covers how we can make our entity move. And actually, if we go back to Unity and enter play mode, you can see that our projectile here are moving toward our target. And once the target is destroyed, they keep going. So if we didn't have any other system, they would keep going for infinity. And that is not good. So if we look a bit closer for this one, the non-guided projectile, if they miss the target, they keep going, and at some point they are destroyed. This is because I've implemented also a limited lifetime component, and I'm doing here something very simple. I'm just having a limit to the time. So if I look at the prefab and take the projectile, this projectile can only live for 5 seconds. If it was spawned more than 5 seconds ago, it will be automatically destroyed. And I'm doing that within a system again. And this system is a limited lifetime system. And for this one, I'm using another type of job. And actually, it's not really another type of job, because the job we just saw a minute ago, the IJobEntity, will actually be code generated. So there is a code generation step with this one, and it will be transformed into the job that we will be using here, which is an IJobChunk. For the IJobChunk, we need to have the list of entities or the list of components we want to manipulate through the job. And we did that with the execute method of the IJobEntity. But for the IJobChunk, we need to do a little bit more work, and we need to use an entity query. So we create an entity query using the System API Query Builder, saying we want all the entities that have the component limited lifetime, and we get several type handles. So this is a reference to the component type of the type limited lifetime, and we need also the entity handle to be able to use the IJobChunk. We provide a few requirements, so we need to at least have one entity that matches the query, and we also need the command buffer singleton to be able to create our singleton. We create our command buffer, we update again our type handle. In the same way we update the component lookups, we need to update the type handles. And we declare our job. So the declaration doesn't differ much from previous jobs. The only thing we need to pass in here is the query itself. And we will schedule the job using the query and the state dependency. As part of our data that will be manipulated through the job, we need to pass in the delta time to be able to decrease the time to live of our entity. We need to pass in the entity command buffer, and in that case we are using an entity command buffer in a parallel job, a multi-threaded job. So we are using the entity command buffer and passing it as a parallel writer. So that's the key takeaway you need to have. If you want to use an entity command buffer in a parallel context, you will need to pass it in as a parallel writer. And we pass in the component type handle and entity type handle. Now, for the job itself, I agree it's a bit more verbose. There is more stuff to write, but I think it's important for you to understand what actually happens behind the IJobEntity, which is kind of a sugar coating all this code. The IJobChunk, as the name implies, will iterate over chunk of entities. So the entities are stored in chunk of memory. I have another video about that if you want to have a look and have a better understanding on how the memory layout of ECS works. But basically, there is a small bag of entities that can go up to 128 entities, and the job will run one bag after another and iterate over one bag of entities after another. We get the entity type handle, we get the component type handle for the limited lifetime, the parallel buffer, and the delta time. The execute method doesn't have parameters related to the component themselves. What we get instead is the archetype chunk, the unfiltered chunk index, the use enabled mask, and chunk enabled mask. So these are used for the enabled components, which we don't have here. And this one will be used, as we will see, for our command buffer. The first thing we need to do is from our chunk, we need to get the array, so the list of components that match our type handle, and we give it the reference to the type handle and get the native array of limited lifetime component. We do the same thing for the entity type handle to get the list of entities that are part of that chunk, that bag of entities that the job is processing. And then we iterate through a simple for loop over all the entities that are managed by that chunk, so within the bag of entity managed by the job. We can get the lifetime, decrease it, and reassign it. So here, same thing. When I'm doing this, I'm actually getting a copy of the data because it's a struct, it's not a reference. So I'm decreasing the value and reassigning back to the component within the array. And if the time is below 0, meaning that the entity has exceeded its lifetime, I simply use the entity command buffer to destroy the entity. And since I'm using it as a parallel writer here, because I'm in a parallel context, I need to be able to order deterministically my commands. And for that, I'm using the unfiltered chunk index as an additional sorting key. So that means that if I have several chunks or the job runs in parallels on different chunks at the same time, it will still be, the command buffer will still be able to order and do the command in a deterministic manner. So whatever the order of the commands are queued in, it will still execute in the same or predetermined order based on that unfiltered chunk index. And that is our limited lifetime system. One system we didn't have a look at is the kill system, where I will be using again an IJobEntity, but I will also be using a command buffer to destroy my enemy entity. And that allows me to show you, so same thing, we have the usual stuff of scheduling, declaring the job, getting the singleton for the entity command buffer, again using the parallel writer here. So I have the explanation here. And this time, within the IJobEntity, for us to be able to have an entity or a sorting key for our entity command buffer, we will use this syntax, the chunk index inquiry attribute on the parameter named chunk index inquiry. And we will also put in the entity because we need to know which entity we want to destroy. So that's how you can use also the command buffers within an IJobEntity and not have to do all kind of work that can be a bit too much to write for simple cases. And now we can check out the last system, which if you take a look at the prefabs and look at the projectile, you will see in fact that the projectile itself contains physics particles. So all you're seeing here are VFX, particle systems. And same thing for the explosion. Actually, as part of the projectile, I have another prefab that is the impact. And this impact also has a particle system. So this is a very, very short and very simple introduction to our way we can communicate between ECS and GameObjects, because as you may know, ECS is not yet full featured. So there are things that we cannot do with pure ECS, like visual effects, like sounds, and like animation that we will see in the next episode. And the way we do that is to have an association or a link between an entity and a game object. And in fact, in some cases, Unity does it by default, like for the VFX or particle system that works also for VFX graph. And it will automatically, if there is a particle system, create a companion game object. That's what they call it. And it will spawn the game object at the same time it spawns the entity. It works for some mono behaviors. It does not work for all of them. So in the next episode, what we will see is how we can make it work for every single component, even the one we defined ourselves. So we can have a way to work with both entities and game object to actually manage a full-featured game and not just a game with no sound, no VFX, no animation, which can be done, but may not be as fun. I know there was a lot of stuff to cover today. Hopefully you did manage to enjoy the video. If you're still there, hopefully that's the case. Thank you for watching again. Don't forget to like and share the video if you find it interesting. And if you want to support the channel and support me to make more tutorials like that, you can support me directly on Ko-fi through a single donation or monthly subscription. Or you can also use the asset store link in the description, which is an affiliate link and will help me to support the channel. There is actually plenty of sales. Don't forget about the publisher of the week also. Follow me on Twitter if you want to be reminded of that. I post a tweet every week about that. And see you in the next video for animation and making ECS and game objects work together. See you in the next video.